Hello, my name is Xue. Today I will present KneeScale efficient resource scaling for serverless computing at the edge. Serverless computing is a promising paradigm for delivering services to the Internet of Things applications at the edge of the network. Its event-triggered computation, as well as fine-grained and agile resource scaling, is well suited for a resource-constrained edge computing environment. The workflow of running serverless functions on edge nodes was illustrated here. IoT devices generate events that trigger the execution of short-lived functions on edge nodes for data processing. In this research, we focus on the resource scaling for serverless computing on the edge nodes. Existing serverless computing platforms rely on general-purpose autoscalers such as horizontal pod autoscaling for resource management. These autoscalers adjust the number of function instances based on a user-specified resource utilization target. Kubernetes implements HPA as a control loop that periodically monitors the average resource utilization of currently running function instances. With the monitoring results, it then automatically scales the number of replicas based on the ratio between the current resource and desired resource. However, it is indeed challenging for end users to find optimal resource utilization target for diverse functions, and such an approach can perform poorly in a resource-constrained edge computing environment. The goal of our research is to find an efficient way to manage resources at the edge. The challenges are user need to define resources utilization target. It has to deal with dynamic workload conditions, and most of edge nodes have resource budget constraints. Let's talk about the motivation of the research. It is common to see that computer systems reach a point at which the relative cost to increase resource allocation is no longer worth the corresponding performance benefit. These needs typically represent the trade-off points between performance and resource cost. As a case study, we analyzed the performance of float operation function from the function benchmark using OpenFast platform. As shown in the equation, we define a performance score as the ratio of throughput and average function latency. The figures show that initially the performance score increases sharply as more replicas are allocated, but after a certain point, the gain in performance score keeps getting smaller with a given performance data for various resource allocations. The need point can be detected by utilizing KNeedle, a general need detection algorithm. For more detail about KNeedle algorithm, please read their paper. In this case study, we demonstrate that HPA-based resource allocation significantly underperforms compared to need point-based resource allocation under resource budget constraints. We use Hey to invoke float operation function with 20 concurrent workers for a duration of 15 minutes. We assume a resource budget constraint of 1,000 replicas on the cumulative resource allocation for the given function. To evaluate HPA performance, we set CPU utilization targets to be 30, 60, and 90%. To evaluate need-based resource allocation, we set the replica count to 34, which is the need point detected by KNeedle algorithm as shown in the previous figure. The figure A shows that the cumulative performance score of HPA 30, 60, and 90 are significantly lower than that of knee-based resource allocation. The cumulative performance score is the sum of performance scores accumulated so far at a given sampling interval. We also observe that high CPU utilization targets of 60 and 90 will lead to high function latencies as shown in Figure B. To this end, we designed and implement KneeScale. Our hypothesis is that running serverless computing systems at such a knee point can maximize the performance under a given resource budget. The key design goals of KneeScale are as follows. 1. Detect performance knee point for an ad hoc function on the fly without prior performance data. 2. Minimize the overheads of knee detection. 3. Adapt to dynamic workload conditions. The KneeScale architecture comprises two main components, performance monitor and the KneeScaler. The performance monitor periodically measures service function-related performance metrics from Prometheus, and Prometheus subscribes the metrics from OpenFast API Gateway. It also keeps track of the invocation error rate and CPU utilization of the function instances to decide when to trigger resource scaling. The KneeScaler component is responsible for on-the-fly knee detection and resource scaling of the running functions. After the desired replica count being calculated, it uses Kubernetes API to allocate the required number of replicas for a given function. Then let's talk about how does the KneeScale work in detail. The KneeScaler component is invoked conservatively when the invocation error rate is greater than 0, indicating the need to scale up, or when the rate of decrease in the CPU utilization is higher than a threshold, indicating the need to scale down. In order to handle dynamic workload efficiently, the KneeScaler reuses previously detected knee values under similar workload conditions. And how does KneeScale detect the knee point on the fly without prior performance data? The algorithm takes two input parameters, BL and BR, which denote the left and the right boundary of the search space. Since the K-needle algorithm requires at least 3 data points to find a knee point, we collect the performance data for 3 resource allocations given by BL, BR, and the middle point of BL and BR. We set initial search direction to the left. In each iteration, the search direction remains unchanged if the most recent data point C last is detected to the knee or knee is not found. Otherwise, we start exploring resource allocation in the object direction after reciting BL to C last if new search direction is right, and reciting BR to C last if the new direction is left. We sample the next resource allocation as the middle point between BL and BR, and the search stops when BL is greater than BR. For more detail about the aforementioned algorithms, please read our paper. Then we talk about the evaluation of KneeScale. We use four competing techniques. The first one is Open Fast Built-in Scheduler. This is the default auto-scaling mechanism provided by OpenFast, and it is triggered when the invocation rate is greater than 5. The second one is horizontal pod auto-scaling provided by Kubernetes. The third one is KneeScale hill climbing. Initially, it will allocate one replica to a given function and incrementally increase the replica count until the cluster capacity is reached. Finally, the K-needle algorithm is applied to detect the knee point. KneeScale random search. In this approach, the replica count is randomly selected, and the K-needle algorithm is applied at each exploration step. The search stops when the knee values remain unchanged for 3 iterations. And our testbed is built on 4 virtual machines. On each of the virtual machine, it has 8 CPU cores and 16 GB RAM, and each virtual machine representing an edge node. We use function bench as our workload benchmark. As shown in the table, we run our experiments with 5 representative functions from different application scenarios. Let's look at the resource scaling results under stationary workload. KneeScale takes about 10 sampling intervals to find the knee point for the various workloads, whereas KneeScale hill climbing takes the longest time to find the knee point due to its incremental search process. KneeScale random search does not find a reliable knee point in most cases. OpenFast built-in scheduler shows extreme behavior for different workloads. We can conclude that KneeScale binary search can find a knee point accurately and efficiently. In this figure, we show the maximum cumulative performance achieved under a resource budget. The maximum cumulative performance is the cumulative performance measured at the end of the experiments. Results shown are an average of 3 runs. KneeScale binary search achieves the highest cumulative performance score under resource budget. And how does the KneeScale work in dynamic workload? For the generation of dynamic workload, we randomly selected 2 days workload pattern from the Azure Function Trees 2019 and sampled every 20 minutes to get about 2 hours of dynamic workload. KneeScale can adapt quickly to workload changes. Likewise, we look at the maximum cumulative performance achieved under the dynamic workload. KneeScale outperforms HPA and OpenFast built-in scheduler by up to 32 and 106% respectively. Finally, let's talk about the conclusion of this paper. We presented an adaptive autoscaler, KneeScale, that efficiently scales service functions under resource budget constraints in edge systems. Experimental results show that KneeScale outperforms existing autoscaling techniques under resource budget constraints for both stationary and dynamic workloads. In our future work, we will evaluate and further enhance KneeScale for large-scale and heterogeneous settings. Thank you. Then I can take some questions. Thank you.